We are ready to do lab number 2. So in lab 2, we are interested in basic circuit laws. And in basic circuit laws, basically we are interested in Ohm's law, KVL, which is Kirchhoff voltage law, and KCL, which is Kirchhoff current law. So those are basic laws. We need to validate those laws in this lab. We wanted to make sure that those laws are valid. That means we can use them to solve for circuit problems. Now, let me list the lab objectives. The first objective of this lab is for the students to experimentally validate Ohm's law, Kirchhoff's voltage law, KVL, and Kirchhoff's current law. So by validating those laws, you will be convinced that you can use those laws to solve for circuit problems. Basically, and by validating those laws, the second objective will be to apply Ohm's law, KCL, and KVL to solve for circuit problems. Another objective of this lab is to be able to determine the number of meshes, nodes, branches in the circuit. Also, you need to be able to experimentally plot data using MATLAB. So basically, you will be collecting data within the first experiment, and you will be able to plot this data using MATLAB. Also, you need to know how to do DC sweep analysis using BSpice. And you're going to do that to validate basically Ohm's law using circuit simulation software. So not only are you going to be able to validate the data experimentally, but also you will be able to simulate the data. Linking the simulation to the experimental data is extremely important for engineers, because usually engineers will understand the theory. They will need to simulate the circuits or the systems. Then they need to build those systems as physical systems or physical circuits. So this is a very important skill for you to have, is to be able to build confidence with the circuit simulation software. It's a very important skill engineers need to have. Also, you need to be able to measure voltage, current, and resistors using DMM. This particular skill is carried over from lab 1, but we need to make sure that you know how to measure voltage, current, and resistors. Current usually is cumbersome for students, so pay attention to how you're going to measure currents using the DMM. Remember that voltages are measured across the element, the currents are measured through the element, and resistors are measured across the resistors. You can't measure the resistor when it is connected in the circuit. To measure a single resistor, you have to remove it from the breadboard or from the circuit. So let's look at the first experiment. The first experiment is to validate Ohm's law. Basically, if you have a resistor like this is the symbol for the resistor. The resistor will have a voltage across it and a current through it. You must follow the passive sign convention. That means the arrow of the current enters the plus polarity of the voltage. What's the meaning of Ohm's law is that as the current goes through the resistor, the electric energy drops, because this is the high end, this is the low end. As the positive current flow, the voltage drops. That means the energy drops, the electric power drops. That means this resistor converts the electric energy into something else. Typically, in the lab resistors that we have, the 5% resistors that we have, the electric energy is converted into heat. So this is a very important physical meaning of Ohm's law. It says that as the current flows through the resistor, the electric energy is converted into another form of energy. And mathematically, Ohm's law expressed as V equals I times R. So V equal IR. As the current flows through the resistor, the voltage will drop. The energy is converted. So instead of using the resistor, we can use the term conductor, where conductance is 1 over R, 1 over the resistance. So using the conductance, Ohm's law is defined as I equals to V times G, where G is 1 over R. Right? So if you divide by R in the top equation here, you have I will equal to V over R, but 1 over R is G. So I equals V times G. That's also Ohm's law. Now, if you come to this first equation and you differentiate dV, di, differentiate the voltage with respect to the current, assuming the resistor is constant, then we can say that dV di will equal to R. And if we say that delta V over delta I, that's the slope, delta V over delta I gonna equal to R. Now it's very important to know that when you use Ohm's law, if the voltage is positive, the current got to be positive. If the voltage is negative, the current got to be negative. So if we plot the voltage versus the current, we're gonna have the straight line. The slope of the straight line gonna be R. Here we have delta V over delta I is the slope. So it's V versus I. And you can see that we can have negative voltage. When we have negative voltage, when the voltage is negative, the current is negative. And when the voltage is positive, the current is positive. So instead of doing it dV di, we can say that we're going to do di dV. So from this equation here, we can say that di dV will equal to G, where G is the conductance, which is 1 over R. So if you plot the current versus the voltage, you still have a straight line, but the slope of this straight line going to be G. Usually in physics and in high school, you've seen this curve or this plot. In electronics, we like to plot I versus V. When we take electronics, we are interested in the conductance of the devices, of the electronic devices. So we plot I versus V. Right? So what's the current going to be as a function of voltage? It's a little bit different than what's the voltage going to be as a function of the current. The curve here, or the straight line here, is basically the resistance. The curve here is the conductance. But it's the same concept. Again, if you have a positive voltage here, you get positive current. And if you have a negative voltage, you get a negative current. In this lab, in this experiment, what we're going to do is we're going to build this simple circuit. We're going to have a power supply, and we're going to connect this power supply to a resistor. Here I'm using 2.2 k ohm resistor, but it can vary. I change my values from one semester to another one. We do that every semester. So here we're gonna use 2.2k, but this value can change depending on what your assignment is. Now, because we have programmable power supply, this voltage source gonna be adjusted. We can adjust that. So what we need, or what we're gonna do, is we're gonna change this power supply from 0 to 10 volts. Then from 0 to negative 10 volts, we're going to measure the voltage, and we're going to measure the current at the same time. We're going to measure the voltage and the current of the resistor at the same time. So we're going to use two DMMs, one DMM to measure the voltage and one DMM to measure the current. So what you're going to do in this experiment is that you're going to build a circuit, then you need to hook the DMM that measure the voltage across the resistor, which is the same as across the power supply. Because when we measure voltages, we measure voltages across. Now when you want to measure the current, you want to break the resistor from the top, from the circuit, and then connect the DMM from the circuit, from the top to the resistor. The reason is you want to see, you want to visualize, and this is extremely important, you want to visualize that the current going through the DMM is the same as the current go through the resistor. You want to make sure that when you measure the voltage, you configure the DMM using the voltage measurements. And when you want to measure the current here for the second DMM, make sure that you use the current's measurement configuration. To measure the voltage, you use a different inlet than when you want to measure the current. And you want to make sure that you configure the first DMM to measure voltage, and you configure the second DMM to measure the current. So when you carry this experiment, by varying the voltage from 0 to 10 and from 0 to -10, then you will be able to have this over here. You want to plot I versus V, so the slope going to be 1 over R. And you want to have this plot in MATLAB. So I want you to basically plot the data points on MATLAB and then compare it with the BSpice simulation. So this is the first experiment we're going to have, which is basically validating Ohm's law. And the data should match the BSpice ORCAD simulation. In the second experiment, we're going to validate KCL and KVL. So let's start with the KCL, stating what KCL is. And to do that, I need to define a node. A node is basically defined as a point where two or more elements are connected. So in the electric circuit, you want to look at a point where two or more elements are connected. So if this is a circuit that we have, this particular circuit has 4 nodes. Let's look at the first node. The first node located at the top here. At this node, we're going to have this voltage source is connected to this resistor. They are connected at this point. There is another node in the middle here. At this node over here, we have 3 elements are connected. This resistor, and this resistor. By the way, each element is called a branch. Branch is basically like, an element, 2-terminal element. So this branch, and this branch are connected at this particular point, so it's a node. This is the third node we have here, where you have this resistor and this voltage source are connected. So this is the third node we have. There is one more node located at the bottom. So the whole thing at the bottom is a node. And people sometimes get confused because the definition says it's a point, but we don't see a point here. We see like 2 wires or a big wire. Right? But this wire can be crumbled or crushed into a single point. So if you crush it into a single point, this voltage source will be connected here, this resistor will be connected here, and this voltage source will be connected here. So this is a node. We call it the ground node, right? And the idea is that a wire is a node, still a node. The whole wire is a node because it's not a branch, it's not an element. It's just a wire. It's a short circuit, right? So it's part of the node. You can always crush it into a single point. You can't crush a resistor into a single point or a voltage source into a single point, but you can crush this line into a single point, so it's a node. Basically, we have 4 nodes in this particular example. Now let's state KCL. KCL says that the algebraic sum of the currents at a node equals 0. Algebraic sum means to add. So if you add the currents at a node equals 0. Algebraic sum means to add, but you're going to preserve the direction or the sign of the current. So if the current enters the node is positive, then the current leaves the node going to be negative, or vice versa. If the current leaves the node is positive, then the current enters the node is negative. Right? You want it to preserve the sign. Then when you sum the currents at a node, algebraically, it should equal to 0. So we can state that mathematically as the sum of the currents equals 0. This is KCL. I like this form, but I like a better form of it. I can always say that the algebraic sum of the currents entering the node will equal to algebraic sum of the currents leaving the node. Over here, you make all the entering currents are positive and all the leaving currents are positive, and they're going to be equal on both sides of the equation. This particular equation is easier to visualize, while this particular equation is easier to solve for systematically, which you might see later on when you apply nodal analysis, for example. If you look into this example here, we have a node, and here we have I1 and I5 enter the node, while I2, I3, and I4 leave the node. So if you use the first equation, you can say that I1 plus I5 minus I2 minus I3 minus I4 equals 0. That's using this equation. If you want to use this equation, you can say that I1 plus I5 will equal to I2 plus I3 plus I4. The sum of the currents in will equal to the sum of the currents out. So to do KVL, Kirchhoff voltage law, we need to define loops. Loop is any closed path in an electric circuit. So look for any closed path, it's going to be a loop. A mesh is any loop that doesn't contain any other loop within it. So the mesh that doesn't include any loops in it. Let's look at example. If we have the same circuit we have over here. So this circuit has 3 loops and 2 meshes. Let's look at the loops. The first loop is the outer loop. Basically, if you look around this particular path here, it's a closed path. This is called loop number 1. But loop number 1 is not a mesh because there is another loop within it. It actually has 2 loops within it. For example, this is the second loop, which is the first mesh, because this mesh doesn't contain, or this loop doesn't contain any other loop within it. The big loop has mesh number 1 within it. So loop number 1 is not a mesh, loop number 2 is a mesh. There is another mesh, which is loop number 3, which is this loop. That's also a mesh. So we can call it mesh 2. Usually meshes are the windows in the circuit. So if you look into the circuit, there is 2 windows. Here is window number 1, here is window number 2. Those are the meshes. Meshes are the windows in the circuit. So now we are ready to state KVL, Kirchhoff voltage law. So Kirchhoff voltage law states that the algebraic sum of the voltages around any loop is 0. So if we're going to sum the voltages around any loop, it got to be 0. And we're going to do algebraic sum. So we have to preserve the polarities of the voltages. We have to keep track of the voltages or the polarities of the voltages as we add up the voltages around the loop. Now KVL has a very important physical meaning to it. It comes from the conservation of energy or conservation of power. Remember, voltage is the energy exerted in 1 coulomb. So if you say that this power supply will add V volts, which is energy, then this resistor must use that energy. This resistor must use that energy so that the sum of the voltages around gonna be 0. The same thing gonna be applied here, right? So the voltage here plus the voltage here, which is the energy on 1 coulomb plus the energy on 1 coulomb plus the energy of 1 coulomb should be 0, because it's basically conservation of energy kind of thing. So mathematically, it can be expressed as the sum of the voltages equals 0. That's your KVL. The sum of the voltages equals 0, but you keep in mind that it's the algebraic sum. You have to keep track of the polarities of the voltages as you add the magnitudes of the voltages. So in this lab, we're going to build this circuit, and we're going to basically validate KVL and KCL. And later on, I will also ask you to validate the conservation of power law, which we also did that in lab number 1. But what's important here is to validate KVL and KCL. Now keep in mind that the value of those resistors and voltages change from one semester to another one, but it's going to be a very similar circuit, very similar concept. So what we're going to do here is when we apply KVL, we have to basically be systematic. So the first thing is, in my approach, my way of doing it is I will always sum the voltages in the clockwise direction. So if I'm going to sum voltages, I'm going to sum the voltages in this way or in that way. It's in the clockwise direction. It's a systematic approach. This is the way I do it. Most textbooks will do it this way. It's better to have a systematic approach when you apply KVL. The second systematic approach is if I enter the plus polarity, then I'm going to add. And if I enter the minus polarity, then I'm going to subtract. So if this is the circuit we have, and we're going to measure all those voltages very easily, right? So you can measure all the voltages easily. You're going to basically use the DMM to measure the voltage across this voltage source. We call it VS1. The voltage across this resistor, I call it V1. The voltage across this resistor is V2. The voltage across this resistor is V3. Finally, the voltage across this voltage source, we call it VS2. So once you measure all those voltages, you need to validate KVL. So when I come through the big loop over here, if I'm going to sum the voltages around the big loop over here, so what I will do is as I enter the minus polarity here, because I go clockwise, so when I enter the minus polarity here, I'm going to subtract. I'll subtract 10 volts. I'll say minus 10 volts. Then I will go to the second element, which is R1. I enter the plus polarity as I go clockwise. So I will say plus V1. Whatever I measured for V1, I'm going to say plus V1. Then I will go to this resistor, which is R3. I enter the plus polarity, so I will say plus V3. Then I will enter the plus polarity of VS2. I will say plus VS2 equals 0. So if you measure those values and you add them up, it's going to be 0 or very close to 0. Because remember that instruments have some precision and some error, right? Due to the calibration of the devices, the calibration of the DMMs. So when you add up those voltages, in theory it should be 0, but it's going to be very close to 0. So the error is so small, and because of that you were able to validate KVL. You can also do it for the second loop. Basically you're going to add those voltages, so you're going to say minus VS1 plus V1 plus V2 equals 0. You're going to validate that for the second loop, and you're going to do that for the third loop also. So you're going to say that minus V2, because I entered the minus polarity here, I will say minus V2 plus V3 plus VS2 equals 0. Basically, you will validate KVL. Now, to validate KCL, first of all, you need to measure the currents at every node. So you're going to come to this node. You need to measure IS1 and I1. So the way you want to measure IS1 is to break the voltage source from the circuit and connect the DMM in series here, measure this current IS1. Then you're going to come to this resistor. I would break the resistor from this end, from the circuit. I'll break this resistor here. I will place the DMM over here to measure the current. And remember that the current enters the plus polarity. Then when you apply KCL at this node, you're going to see that IS1 will equal to I1. That's basically the first KCL equation at the first node. When you come to the second node over here, you already measured I1. You're going to measure I2. To measure I2, you're going to break R2 from the circuit and connect the DMM in series with it to measure the current. And then You break this resistor R3 from the circuit, and you want to connect the DMM in series between this node and the resistor, and measure I3. And then when you sum the currents, you're going to see that I1 will equal to I2 plus I3. Finally, at this node, you're going to break this element, which is the power supply, from the circuit, connect the DMM in series, and you want to make sure that the arrow enters the plus polarity. So the plus polarity to measure IS2 should be going from the power supply into the circuit. So when you use the ammeter to measure the current, you want to make sure that the arrow enters the plus polarity again. And now when you sum this current and this current, they're going to be opposite in signs, and if you add them, they're going to equal to 0, because this enters the node and this enters the node. If you add them equal to 0, then this current and this current going to be opposite signs. I3 going to be in the opposite direction or opposite sign of IS2. There is one more node you want to do, which is at the bottom, but you already have all those measured currents given to you. So you know that at the bottom you have IS1 is leaving while IS2 is going in, and IS2 is leaving. So you're going to say that I2 will equal to IS1 plus IS2. And you validate that using KCL by summing the currents at this node, and they should be equal. And by doing that, you basically validated KCL for the circuit. Also, you're going to simulate the circuit using BSpice, and you need to compare the results that you measured with the BSpice simulation. I want you to build that confidence between the simulated values and the experimental value, and how they are related to the theoretical values. It's a very important skill. I want you to basically feel comfortable with that early on. I hope you enjoyed this video and it will help you prepare for the lab. Thank you and good luck to all.